Good afternoon, and welcome to Microsoft's Development Center Copenhagen. I'm Michael Nielsen, and I'm one of the 500 developers here at this campus. So for those of you who are from the outside, I hope you will enjoy your afternoon here with us. This is beautiful weather outside as well. And these tech talks over time has been very much about developing, and one today with Simon is going to also be around the same theme. But next time in December, we're going to do something different because Microsoft is more than writing code. We're also about the process behind writing code. You probably all know that Microsoft was about writing a lot of code, putting it on a DVD after several years, and then sell it in stores. But the world is changing, and Microsoft is moving to agile like everybody else out there. And in that process, we have invited a guy called Donald Reinerson, who's applying lean from the car manufacturing industry to software, and has a lot of influence on the process. And he's going to be here on December 7th to tell us about his research. He's also written several books. This one, Flow, which is really good. So I really encourage you to come back when he is here in December. But now for this, and let's focus on the session for today. So Wednesday we have Simon, who is one of the foremost computer scientists in the world. A lot of you know Simon already. He's a friend of Denmark and has been here many times before. And Simon just spent this morning with Fred's headline and the other friends at DQ, talking about Haskell and other programming languages, and he's going to be back there tomorrow, I heard. So Simon is really focused on functional programming, and I know what really thrilled him was that when these multi-kernel procs came out there, nobody really knew how to put them to use, or it was very cumbersome to really use them in an ordinary programming language. And that's some of the aspects behind Haskell on bringing these kernels to work without having to do something special. Today's talk is not going to be just one tech talk or two. So first Simon is going to talk about type classes, then there's going to be a small break, and then the rest is about type functions. So please give applause to Simon, and welcome to Copenhagen.
Good. Can you hear me? That's good. Well, you're doing me a great honour by coming out in such large numbers. Thank you for tearing yourself away from your screens. I too have come from the code face. Yesterday I was just trying to get GHC to have the regression test clean so we could commit and make a new chunk, but I didn't succeed, so my colleagues are still looking at those last few regressions. So thank you for coming today. I hope that what I want to do is look at a particular aspect of Haskell and I'm going to show you quite a lot of code. I'd really like you to understand the code, and I'd really like you to understand pretty much every line of code you see. So I really don't know anything. Who's actually written Haskell code already in their lives so far? Okay, so about maybe a quarter. So kind of in a way, you're not the guys I'm addressing, right? So the 3/4 of you, I really would like you to understand this. Right, so I'm not going to show anything too scary, but please ask questions as we go. Don't save up questions for the end. If you ask questions as we go along, you'll make me feel that you're listening and you're kind of engaged. And if you just all sit there and look awed, then I shall be very depressed. Right? So, let me just start by giving you a brief feel for what being a programming language designer is like. Programming language is a two a penny. Here is the typical life cycle of a programming language. It has a user base. This is the user base here. The Microsoft languages are somewhere way off the scale here, but user base is one. This is a log scale, right? User 1, and after 1 year it dies, goes to 0. This is the hundreds and hundreds and hundreds of programming languages. PhD students do this. There are 3 languages in your PhD. Now, this is a more typical, a successful research project in research is you just die more slowly, right? So here you last 5 years and you maybe get some tens of users. This is what happens to real languages like Ruby or Perl or C#. They pass a sort of threshold of immortality beyond which they can't be allowed to die because there's too much code written in them. In fact, Richard, it is Richard, isn't it? Yes. Your Pascal-like language, with the millions of lines of code, you're way past the threshold of immortality. right? Can no longer be allowed to die. We have to keep you alive forever. Now, here is some what happens to languages designed by committees, right? 0 users. Haskell is a language that was designed by a committee back in 1990 or thereabout. But curiously and somewhat unusually, this didn't happen to Haskell. Here's what's happened. We kind of started in 1990, got to the kind of the slow death stage, in which you plateau at a few hundred people, and then it looked as if things were pootling along. Then suddenly in the last kind of, well, certainly the last decade, if not the last 5 years, things have picked up a lot. That's partly why I'm here. I guess 10 years ago, I wouldn't be here probably. Chances are. So something funny has happened. I don't quite know what it is, but I think it's good. And here's another way of looking at what's happened. This is a site called langpop.com that I've only looked at twice in my life, but once was in 2008, and here's what the figures showed. It's a site that looks at open source repositories and finds out what languages the stuff people are developing is written in. And here, you can't see this very well, but I'll tell you, at the top here, there's Java and C and C++ and PHP, right? And down here, Shell, assembly language, Delphi, Lisp, Cold Fusion. Cold Fusion? Whoa, Haskell, we're on the scale, right? Research languages don't get to be on pictures like this, so this is fantastic, you know, on the chart. But what I found even more amusing, they have another chart that mines the discussion groups, what people are talking about, blogs and websites and stuff like that. And here is what it looks like. So Java, C, C++, Python, PHP, Haskell is number 6. So in summary, Haskell is a language that everybody talks about and nobody uses. But I think it is quite fun. I mean, in some ways that is part of the reason for this talk. Is Haskell is a kind of laboratory for ideas, right? It's a kind of pure setting which we can develop I think they're interesting ideas. And then sometimes they can make transition into real-world languages, like generics is one example. They didn't arrive just in Haskell, but within functional programming languages is where generics really showed up big time for the first time. Garbage collection, perhaps also. Lisp invented garbage collection back in the midst of time. What else? Workflows in F#. That is an idea that started in Haskell in the form of monads. So there are quite a few ideas in Haskell. Being purely functional, controlling effects, laziness, and lots of stuff to do with parallelism, none of which I'm going to talk about today, because I want to focus on one thing, which is on type classes. Because my hope is that by looking at one thing in more detail, you'll have more fun than if I tell you a tiny bit about a lot of things. Okay? So we're just going to delve into this thing called type classes. So that's relates to the title of the talk, because this is a Haskell type class. Sounds as if it might be something to do with a Java or C# class, and actually they're really not quite the same thing at all. So I hope that by the end of this talk, you'll have a much better idea of what the two things are and kind of how they compare with each other. Okay? Right. So now we're going to get specific. We're going to write lots of code. So this is the point at which if you don't understand any piece of code I show you, you've got to start waiting. All right? Because you're coders, right? And it is right, aren't you? It's true. Yeah. Nod. Yeah. Good. All right. So here's a Haskell function. So Haskell people have already seen this before. Can turn off first a slide. I'm just going to show you an ordinary plain Haskell function, no type classes anywhere. This is a function called filter that takes a list and a predicate, that is a function from elements of the list to booleans, and just filters out, just keeps the elements of the list that satisfy that predicate. So this first line is its type signature. Just filter has type, and then the arrows separate the arguments. So it says it takes one argument of type A to bool. That is, it takes a function from A to bool, and square brackets means list of, and a list of values of type A, and returns a presumably shorter list of values of type A. What is type A? Well, it doesn't matter. Filter will apply to a list of integers, a list of booleans. It's just like generics in C#. So how do we find filter? So we just define it by pattern matching. So let's see. P is the predicate. That's the first argument. This second argument is the list here. And Haskell's notation for lists are constructed either with, have I got a slide for this? No, yes. Lists are constructed, a list is a data type, and a list is either empty or it's a cons, and you write a cons with a colon, right? So this says a list of A's is either empty or it's a single value of type A, consed onto or followed by a list of values of type A, so it's a recursive type. So here we go. Either the list is empty, in which case if I filter out all the elements, I get an empty list, or the list is non-empty, in which case its first element we'll call X. So this this vertical bar is read like a guard, or if. If p of x is true, because p, remember, is this function from a to bool, p of x is true, then return the list x cons filter p of x's. I beg your pardon, that's right, because I'm keeping x if the predicate holds, and if the predicate doesn't hold, then I just want to filter the rest of the list. Okay? So recursive function. One thing that's perhaps less familiar to imperative programmers is that filter takes a list and it doesn't alter it, doesn't mutate it at all. It returns a completely new list, freshly allocated here. So Haskell programs allocate like crazy, right? We gobble up one list and we allocate a new one. But heck, it's all in the cache. So that's functional programming for you. You don't mutate old lists, you create new ones all the time. What other things to point out? Functions defined by pattern matching. This guard stuff for subcasing, and here's probably the most important thing to remember, is function application is written using because it's so ubiquitous, function application, we write it using the quietest possible notation, namely space. Right? So rather than writing f open brackets x comma y to mean f applied to two arguments x and y, we just write f space x space y. Right? That's just that's a bit of a discontinuity. You just have to get used to it. Sorry. Right. Good. Now, so here's the problem that type classes are addressing. When you write, here's another function, a bit like filter, except it takes an element type or a value of type A and a list of type A and returns a Boolean telling you whether or not this element occurred in the list. So it's called member or element of. Is x an element of the empty list? No. Is x an element of y cons y? Well, if x is equal to y, then yes, otherwise we better see if x is a member of y, okay? Well now, so now we're going to start to talk about type classes and why this might go wrong, but let's just deal with any sort of notation. I've shown you two function definitions now. I just want to check notation, right? Because if you're lost on these slides, you're going to be very lost soon. But I'm hoping it's okay. But I'm so familiar with Haskell, I can't see what the difficulty is. But you can, right? So just tell me. Ask questions no matter how stupid. They're not stupid, right? It's just different. I have trouble with C#, believe me. No, this is disappointing. Very disappointing. And not fulfilling my audience expectations. I'll give you one more chance. Right. Let's see. So, what's the problem with this function? The problem with this function is that it requires this equality thing. But I said this works on arguments of any type. Any type at all. Well, for integers that should be okay, booleans perhaps. What about functions? Because after all, we've seen it. We've got values here of functional type. P is a function. What happens if I had a list of functions? Oh, dear me. Could I ask whether the negate function was a member of the list increment lambda x 0 minus x negate? There's a list of three functions. This is just notation for the function that subtracts its argument from 0. Is negate an element of this list? Well, here it is here, but kind of this is really the same function, isn't it? The function that subtracts its argument from 0. So somehow equality on functions is a semantic notion, right? It's not. So we really should be able to. How can you say are two functions equal? You could apply them to all possible arguments, but that would be a bit of an expensive test. So really, what you want to say is you shouldn't be applying member to a list of functions. Lists of functions are perfectly fine, but you shouldn't be calling member on them. See the problem? And this problem occurs again and again in different ways. Here's sorting, right? Takes a list of values of type A and returns a list of values of type A, but it needs to compare them. Plus takes three values of type A. I'd like it to work on floats and integers and so forth. I'd like it to work on any numeric type, but plainly I can't expect plus to work on functions or even on lists. Or maybe I do want to wait for plus to work on lists, but it's going to work very differently than on other things. Plus is not kind of universal in the same way. Show is like serialize, take a value and turn it into a string. Clearly, how you do that does depend on the type. It doesn't work for every type. Similarly, serialize and hashing. Okay, so this kind of pattern occurs again and again, in which you don't want, in which these types are, if you like, too polymorphic. They claim to work for any type whatsoever, but they can't possibly work for every type whatsoever. So there's various unsatisfactory ways of dealing with this. One is to make some kind of local choice. So you can write A plus B, thinking of A having this kind of type, but locally we see that A is a float, say, and so that when you write plus, it's really just shorthand for writing plus float. And if you look at any occurrence of plus in your program, you could say that's a plus float, that's a plus int, that's a plus double, right? Statically fixed. That is one solution, that's what ML does, in fact. Another kind of solution, which is implemented in, for some of these kind of functions in most object-oriented systems, is to provide some functions for every type. So equality, serialization, and stuff like that, hashing, I think, is provided for pretty much every value. Right? It's a runtime it's a service provided by the runtime. Right? So in .NET, you can take the equality of any two. Am I right? You can take the equality of any two objects. You're supposed to be experts on this. Tell me. Yeah. And it'll say it'll do pointer equality or something ghastly. Right. The trouble is, this means that you could do it for a fixed collection of operations, but what if you wanted to do operations that you the programmer, had invented? Then the designer of the runtime couldn't possibly have known everything to bake in that you would subsequently want to do. So what are we to do? Here's Haskell's solution. It's to say, so I'm switching examples to an example on numerics. The simplest example on numerics I can think is a function which squares its argument. You would kind of like it to have type for all A arrow A, right? But it can't work for every type. So we would like to say something like, for all A that has numeric properties, A arrow A. Does that make sense intuitively? Yeah? So here's how we write the type in Haskell, num A double arrow. So you should think of this being for every type A that satisfies the num predicate, or if you like, or has num-like properties, or is numeric, arrow A. So now, and we do the same kind of game, at least you can see how the notation of this might work out. But we could, for sorting, we require ordering of some kind, for serializing, maybe show, for member, we needed equality. Right? So at least we've got a way to speak in the type language about constraints on the types that are allowed to instantiate this type variable, this generic stuff, right? Now, are these num and all things built in? By no means. These guys here are not built in at all, they're simply declared. And this is what Haskell calls a class. It's more like what C# and Java call interfaces. So the way to declare the num class is this. You say, num, so this is a language construct. You say, it's a keyword. I'm introducing a new class called num on types A, which has, and then you list the type signatures of the operations that numeric values have. So numeric values have a plus, which has type A to A to A, times with A to A, and negate A to A, and so forth. Okay? And then, to make a particular type an instance of num, you say, well, int is a numeric type, and in witness of that fact, you must say, oh right, so to add things, use plus int. To multiply things, use mulint, and so forth. Right? So I'm assuming here that we've got some basic functions down in the right-hand corner that operate in a completely monomorphic way, just on a particular type. So I know how to add ints and multiply ints. And this declaration just says, as it were, the witness or the proof that it is indeed an instance of this class is, and I give the implementations of each of the methods. All right? So far, so good?
What about operations between different instances of the same class?
What about operations between?
Different instances of the same class?
Oh, you mean could I add two floats and then add that to an int? Well, that's a good question. So the plus here always takes, let's do plus. It takes two ints and produces an int. Now, if I then wanted to add that to a float, I would now have an int and a float, and I want to produce a float, and that comes in the next talk, right? So these types here are only going to let you say, well, the type signature I've said here is that it takes the three types, all identical, int, float, 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 no mixing. Okay, so you have the int world and the float world. If you have an int to float function, you can call it yourself, but it's not going to happen automatically, at least not in what I'm showing you here. Okay. Thank you. A question. Another question. Yes. Oh, what's the semantic difference between these two? In the end, it'll turn out that there will be no difference. But the way to think of it is, for every n that satisfies num, NRN. So this part is going to show you the arguments, right? Yeah. So square here has one argument, and that's that n arrow. This part, as you'll see shortly, is going to turn out to be an argument, but for the moment you think of it as a kind of predicate on the type, a constraint on the types that are allowed to instantiate it. Does that make sense? So I don't give an explicit argument that corresponds to that num, and that's the reason for the double arrow. Yeah. Okay? Anybody else? Yes?
In the instance declaration, could you have written the function directly there? In the instance declaration?
Yeah?
Could I have written the function directly there, or have to point to another function as it?
Oh no, could you write the function directly? Oh, you could definitely write, here, a plus b. I don't have to just have a function call here. You can write an arbitrary expression, yes. In fact, you can write an arbitrary function definition. Like, we'll see a couple of examples later, but this function definition that we wrote earlier here, if that happened to be the witness, yes, you could just write it right here. Yeah. Thanks. Okay, so I'm a compiler writer. I don't like being told about sort of language constructs that I don't have some visceral gut feeling for how they're going to be implemented. So I'm going to tell you how type classes are implemented, because I found it's the easiest way to understand what they do. So here's a bit about the implementation. When you write this function, square, for num n, non, the yellow stuff is going to be what the programmer writes. The blue stuff is going to be what the compiler transforms it into. So it adds a secret parameter called d here, right? An extra parameter to square that corresponds to this num guy, right? An extra value parameter. So square now has two arguments. And you should think of this as the v table for numeric things, right? It's the record of functions, the addition function, the multiplication function, the negate function, right? It's just a record of functions. And I'm going to pass it to square. So now that you know that d is simply a tuple or record of functions, now I'm going to pass it to multiply. So multiply now takes a d and then two x's. And what does multiply do? What does star now do? This star we were thinking of as being multiply. This star isn't really multiply, it is merely projection, selection. Yes, it merely picks from d. So star is an argument, is a function of one argument that takes its little record of functions and picks out, say, the third one, because that happens to be the field for the multiply function, right? So it selects the function. So now star applied to d has now picked out the multiply function, which is, so the value of this is a function which, when applied to these two arguments, are the multiplication. Right? Easy. It's just higher order programming. You're just passing a record of functions and selecting from it. Just object-oriented programming, in fact, in a funny kind of way, except the v table is traveling separately. We'll talk more about that later. So, to be concrete then, when you give a class declaration in yellow in the source program, what happens in the implementation is that we're making a data type declaration. So this declares num a to be a data type, parameterized over a, and num is its constructor, right? And then here are all its arguments, but one for each function. So this is the record of functions. And now star, as we're saying, is just the selector. It pattern matches on num and picks out, well, in fact, this time it's the second field. Does that make sense? So I'm hoping now you think, oh, so that's you could almost have written this directly. Turns out this is yellow stuff's much more convenient to write, but you can see it's pretty easy to just systematically generate the blue stuff from the yellow stuff. Does that make sense? Yeah.
So a star is the magic function which always picks out the matching star.
Oh, is star a magic function that always picks out the magic piece, that picks out the second piece? No. Here I wrote star. If I'd written Fugel here, then I would have transformed this into a definition of Fugel, which would be the selector. So the things given signatures here are precisely the selectors. Does that make sense? So the fact that it's star is not at all special, no. It's just whatever you say. And this is just a piece of library code. It's not treated special by the compiler. It just does this systematic transformation. Okay? Any other questions at this point?
So in the blue side, you would see normally lines for plus, for negate, and so on. Right?
Indeed, yes, absolutely. So on the blue side, I've left out plus and negate. That's one for each. Yes. So for everything here, we have a field here and a selector down here. Exactly. And now this fairly simple idea lets you now, wait a minute, so once we get, this is the class declaration. Let me just show you how the instance declaration is translated. I mean, there's only one way you could possibly do it. This instance declaration, instance num int, well, that means this is saying I'm witnessing that int is indeed an instance of num, and I witness that by providing a value, dnumint, I've just arbitrarily called it dnumint, of type numint, which is the record of plus, null, and negate. So it's just completely straightforward. So for every instance declaration, I get a record declaration in the blue stuff, right? And now, to take a particular example, supposing I have f with type int arrow int, and f, so this is source code, negate of square of x. What do? Over here, every time I call negate, remember negate had the type for all n, num n, arrow, double arrow, n to n, so it has an extra argument. So I pass dnumint to negate, and square, you'll remember, had a num thing, so it needed it needs a numint argument. Very good, I've got a numint there. So the compiler just adds the red stuff, and now we have a perfectly ordinary program that just passes value parameters and does record selection. Okay? And that's really all there is to type classes. We just systematically take every function with a double arrow, we give it an extra value parameter, and we make the methods of the class into selectors. Couldn't be easier. It's a very simple idea, but it works in a very nice modular way. Here's an example of what I mean by modular. Supposing I now have got square, and I want to write some square, which takes x and y, and it squares x and it squares y and adds them. How can I do that? Well, I have a pretty systematic translation for that. I say the blue, some square, takes a value parameter of type num n, and what does it do? There it is called d, and it's going to add the result of squaring x and squaring y. So it adds, that's plus applied to d, sort of square. Now square takes one of those dictionary record arguments, the vtable arguments, and so I'll pass this d to both of these guys. And it has to be this d because both of these guys need a num n, and I've got a num n in my hand. So internally in the compiler, there's lots of stuff going on that says, I'm calling a function that needs num n, and you're providing num n. Very good, I'll pass that. Right? So I'm kind of hoping at this stage you might think that if you were pretending to be a compiler, you could take code like this and you could simply write down code like that. And this stuff doesn't have any type classes in. It's just an ordinary functional program with simple data types. It's an ML program, if you like. Any questions at this point? Yeah.
How do you have a good instance of the type? Like that this D, you should make several instances, or you should remove one or?
Oh, do you mean what happens if I get a second instance for numint?
So no, the first question is just because you say that this instance is for ints, the compiler can find automatically that you made an instance in the file.
Yes.
But then the next question is what when you show two instances of the type?
Okay, so if the compiler cannot see an instance for numint, and let's see here. So here it says, I need an instance for numint because I've got to pass it. Look, I've got to find a dnumint from somewhere. So it looks around in its sort of current compiler context. If it can't find one, it complains. If it finds two, it complains as well. Right? So if you make int an instance of num in two different ways, that would be bad because now I don't know which plus you mean anymore. So yes, so there's a kind of overlapping instance check that says, in effect, there's only one method suite, there's only one vtable for any particular class and any particular type. Yeah, and that's very, very important. So there's a sort of unique way of constructing a particular vtable. Okay? Now, here's another way in which things are modular. Here I've shown you how to, you can make big overloaded, these are overloaded functions because they work over many types. Big overloaded functions out of smaller ones here. But you can also do the same with instance declarations. Have a look at this. Remember, supposing we have our class eq here, it has a single method equals with type a to a to bool. Now, supposing, do you remember, if I want to take equality of lists, how can I say instance eq of list of a? Well, if I want to take equality of a list, what do? Well, if the two arguments are empty, it's true. If the two arguments are both conses, I must check for equality on the heads and equality on the tails. What could be easier? But there's a problem, because here I'm taking equality on the heads, so I needed EQ of A, right? So in order to make a method suite or vtable for equality on list of A's, you need to give me a v-table for equality on A's. Does that make sense? How could you possibly do it otherwise? So the way in the source language we express it like this: instance ek double arrow. So think of this kind of like a function, right? If you give me ek, I'm going to give you eq list of A. And here's what it translates into. From the instance declaration here, we get deq list. The name is not important, but its type is important, which is a function from a v-table for ek to a v-table for eq list of A. And how does it work? Well, it takes a v-table for the elements, that's this d, that's of type ek, and it's going to return a v-table for equality on list. So that's just one function. This is a v-table with a vector of 1, right? Because it's only got one method in this class. And that's this EQL function. Here's the EQL function, and it's just the code that we wrote here. And the interesting piece is that here, when I need to take equality on the elements, I select it out of the method suite that I was passed. Okay? And in fact, the translation that went from here to here is very, very, very similar to the translation that went from here to here. So the same game applies. Notice on this corner here, I was able to recurse directly to EQL because it's on exactly the same type. Okay, so the instance declarations are nice and modular. So if I now ask you for, an EQ on list of int, then the compiler can just apply this function 3 times and then onto an equality on int, and away you go. And there's only one way to do it. Oh, you mean if I had 2 lists and they just happened to be pointer equal? It seems a shame to be marching down them, comparing them all the way down. Yes, it does really. But it kind of is a very special case to do with equality. I mean, if I was multiplying 2 things that happen to be the same. So equality may be, in fact, in GHC, in our compiler, we don't make any special case for equality. But you could. You have to be actually a little bit careful, because in Haskell you can have values, you can have infinite lists, right? Because it's a lazy language. So if I ask you, are 2 infinite lists equal, then semantically you have to march down them, and then you never terminate, right? If they were infinite, right? So if you said, oh, they're pointer equal and just return true, then the semantics of the program would have changed compared to the marching down version. Now you may say that the marching down version is a bit stupid. But in general, you have to do that. If you have 2 disjoint lists that are both infinite, then you have to march down them in case they might eventually differ. So you have to diverge, right? So now you're into a very delicate territory about you don't want the semantics of your language to change about whether data structures are shared or not. Sharing is kind of invisible in Haskell. So that's one of them. So you have to be a bit careful with optimization lest you change the semantics. Nevertheless, so GHC, being a practical language, has an operation called unsafe pointer equals. So the places we have trapdoors that say, if you really know what you're doing, you can call this function. They're always called unsafe something. So you have to, as it were, every time you type it out, you think, do I really want to do this? Okay, now, I want to show you one other thing that you can play with this game that is a little, gets you into territory that's a little bit new. So far you can kind of do most of this stuff in an OO language, but here you can't so easily. Let's see, numerics. This num class actually has one operation that I haven't told you about called from integer, and it has type integer, that's a fixed type, arrow A. And literals, this is a sort of de-sugar rule. When the compiler sees 1, a literal 1, it translates that to from integer d of 1. Right? So as it were, it adds an invisible from integer in front of every literal. Because what that means is, and remember, since from integer returns a value of any old type, what that means is that when you write a literal 1, you mean a literal of any numeric type suitable for its context. Right? So here, when I write increment of x is x plus 1, it'd be really annoying if this was fixed to be an integer or a float or a double. Right? It's really nice that if you say x plus 1, this works for any numeric type. But if it's going to work for any numeric type, then I've got to be able to get a constant 1 in the type A. Do you see the problem? So, as it were, I've got the type A, and I say, give me a constant 1 of type double, give me a constant 1 of type A, give me a constant 1 of type list of double, who knows what. And that's what this from integer thing does. Okay? So it's, the unusual thing is that the type we're concerned with appears only in the result, not in the argument. That's something that we'll come back to. And that's how little's adopted. And because otherwise you'd find that functions that you wanted to be kind of overloaded, if you couldn't overload the constants as well, then as soon as you put in a constant, blam, you've lost the polymorphism. Okay? All right. Now, okay, so now I'm going to show you. So far, everything I've shown you has kind of been part of that set of examples that we started with: show, equality, ordering, serialization, all that kind of stuff. And that was this kind of stuff that we said, oh, maybe those could be just about built in. So you're thinking, well, okay, so this is different, but is it any better? So what we discovered is, while we designed type classes for that set of examples, and this general purpose mechanism, we hoped that it would be useful for completely new examples. So now I want to show you a totally new, and to me, completely mind-blowing example called quick check, invented by a colleague of mine called John Hughes. This is kind of mind-bending, but incredibly beautiful, and we would never have thought of it if we hadn't had the type class framework. So here's the idea. Suppose I want to write tests for my program. One thing I might do is to write down properties that I believe my functions have. So here's one. Reverse of x's should be equal to x's, right? You reverse a list twice, you get the same thing. So prop rev is a function that takes a list of integers and returns a boolean, and you expect that prop rev will always return true, right? So it's quite nice to, when you're writing down properties, rather than writing down in some other language, some sort of logic or specification language, it's quite nice to write down properties of your functions in the language itself. So this isn't intended to be a function you're ever going to run at runtime as part of your application. It's part of your test suite. It says, give me, this function should always return true. And the idea is that a test framework might make up lots of lists, the empty list, the list with 1 and 2, a list with 4 and 7 and 9, and try call proprev on it and see if it returns true. So a test framework which would make up lots of test data, call proprev and see if it returns true all the time. Okay? So that's the idea. Here's another property, that if you reverse the result of appending, plus is append, if you append two lists and reverse it, you should get the same as if you reverse the two lists and append them the other way around. Okay? Well, so this function too should return true for any arguments here. Okay, now, quick check is a library which generates the test data. So you sit in the read-eval print loop. So GHC comes with a little read-eval print loop. So here's the prompt, GHCI, and the user here has typed quick check proprev. So you can see the quick check here is taking this function as an argument, and internally it's applying it to lots of data, and then it says, okay, I applied it to 100 different lists, and they all return true. And here I'm applying quick check to proprev at this function, and it's applying the function to lots of different data, and it always returns true. Okay, so there's something fishy about this. What is fishy about this stuff here? Think about types. Think about the type of so quick check. This is not a language construct. This is not some built-in framework thing. This is simply a Haskell function defined by a library. But what's its type? Tell me something about what its type must be. Anything about its type. The function quick check. Internally, it generates random numbers for sure. Right? Right, so here, proprev, I'm giving it a function with one argument, with one arrow, as it were. Here, I'm giving it a function with two arrows, and somehow, quick check was clever enough to figure out, oh, this function with two arrows needs two randomly generated arguments, and this function with one arrow needed one randomly generated argument, right? So quick check can't have the type, for all A and B, A arrow B arrow stuff, because that would only work for this guy. So the type of quick check is very curious. And here's what it is. Quick check takes any type A, which is testable, and this I/O thing. Don't worry about this I/O thing. It just says I might do some input-output, which means generate random numbers and print the output here. I might do some input-output and finally return unit. I'm not interested in the result, except for this side effect on the world, right? That's how Haskell expresses I/O. Okay. Okay, so now fasten your seatbelts. This is how this testable class works. So testable is a type class, just like null and unique, with one method, test. And what does test do? It takes this value that we're supposed to be testing, think of it as a function that we're supposed to be testing, and a supply of random numbers. And the idea is it's going to apply this function-like thing to randomly generated arguments and see if it returns true every time. And if it did return true every time, we'll return true. If not, we'll return we won't. Okay? So that's the idea of what test does. Now let's see. If we gave it not a function at all, supposing we just gave it a boolean, we gave a boolean to testable, right? So we applied quick check to true, if you like, rather than applying it to a function at all. Supposing we applied quick check to true, right? So it was a nullary function, if you like, that took no arguments. Well then, does this function of no arguments always return true? Well, it does if and only if this A guy is true. Right, so the testable instance of a boolean is very simple. It doesn't need any random numbers because there's no functions involved. It's a nullary function, no need to generate any test data. This is the base case. Are you with me? Okay, now look at this. How would I say if a function from A to B was testable? Well, let's see. Test, remember, takes the value and a random number supply. So test fr, so there's the function. It has type A to B. What am I going to do to this function? Well, I've got to make up some arbitrary data of type A. So here is RB of R1. R1 is a random number supply. So I take the random number supply, this guy, and I split it into two. So there's a split operation that takes a random number supply and gives me two random number supplies. Imagine that the random numbers form a tree, right? So I just get two random number supplies. So RB, which we'll see in a sec, is going to generate a value of type A to give to F. Once I've got this value of type A, that's a piece of test data, I give it to F. F takes an A to a B. So what do I have now? A value of type? A value of type? Altogether, a value of type B, right? Function of type A to B, I give it a value of type A, I get back a value of type B. Hooray! What do I do? How can I test the value of type B? I have a function to do that. It's called test. So I'm going to call test on the value of type B. And I, of course, test needs a random number supply, so I'll give it R2, the other half of the split. But in order to do that, that's like my equality thing, when I, way back here, when I did, what happened to my equality? Yes, here. When I called equals on the element type, I needed to say, I need equality on the elements. So here I need that B is itself testable, so that I can call test on this value here of type B. Last thing, how do I generate the arbitrary value of type A? So I have another auxiliary class here, arbitrary, with one method of type called RB that takes a random number supply and produces a value of type A. And I think you can see that if you can make instances, like you could say instance RB of int, right? How do I make an arbitrary int? Well, take the random number supply, pick a random number, and make it into an int. How do I make an arbitrary pair? Well, I pick an arbitrary first element and an arbitrary second element to make a pair. So I think you can imagine how to make arbitrary produce test data. And there's a whole little science there. You know, look up the literature on how to generate test data, and the instances for arbitrary express your test data generation. But what's amazing then is that this is the whole core of QuickCheck in sort of like 10 lines. We're essentially doing recursion over the type. Right? Because back here, I'm going to give to QuickCheck a function that goes int arrow, this is brackets, list of int arrow bool. Right? And we're going to do recursion over the type to generate test data for both of those arguments. Oh, well, so if you wanted arbitrary, say, for a list type, then you definitely want to sometimes generate an empty list and sometimes not. Good, so sometimes you want to specify sort of specialized test generators. And read the quick check paper. They have a nice little domain-specific language for writing test data generators. So it's actually, the fact that it's in your hands because it's programmable means you can, because sometimes maybe if you're writing a sort function, or there are some functions where it matters, if you're not careful, you'll generate lots of data that immediately doesn't pass some predicate, and so it's not useful to you. So you need to generate lists that are mostly sorted or something. So you may need to skew your generation of test data in order to actually test your function. Otherwise, you spend a lot of time testing cases that turn out to always test the same branch of the code. And so the quick check provides you with a bunch of other functions that let you generate suitable test data. But I wasn't going to, yes. The point of this slide is really the sort of orgasmic moment to which you realise that this class mechanism lets you do something that we never dreamt of when we first defined it. In fact, it's really rather amazing that you can do it at all. In fact, this quick check technology has since moved over to Erlang and other languages because it was such a cool, interesting idea. Other questions about the slide?
You have 3 arguments. Do you have to change the instance?
No, that's the good question. What if there are 3 arguments? So here, prop where that has 2. If there were 3, no, all that happens with 3 is that I get to crank this instance declaration twice. Do you remember when I said, if I wanted a dictionary for equality of list of list of list of int, I would apply, the compiler would apply this instance declaration 3 times. In just the same way, if I have a function of, actually I think I haven't, there's one thing I haven't told you strongly enough, which is that this arrow, we should think of this as int arrow open paren, list of int arrow open paren, list of int arrow bool close paren. That is, that is really a function of one argument that returns a function that takes another argument. You see what I mean? So if there are 3, it's really something arrow open paren, something arrow open paren. Right? So what that means is that the recursion here on this single arrow is enough to crank its way down all those nested arrows. I don't know how I could say it any more clearly than that, but it works just fine. Okay? So this is the hardest piece of code you're going to see. So if it hasn't fully sunk in, you should just look at the quick check paper, because it's a thing of beauty. You kind of once you see it, you think, now I can die. Oh, this random number supply. So there's a lot of splitting of this random number supply going on. You're right. So the random number supply isn't really a tree that you manufacture in advance, because then you would probably only look at little bits of the tree. It's a sort of virtual, it's a lazily constructed tree. Remember, Haskell is a lazy language. Or another way to think of it is, imagine this random supply was really represented by a seed, right? And split just generated 2 seeds, right? And now you split those, they generate more seeds. Now you have to be a bit careful to make sure that they're somehow independent according to good random number principles, and that's a whole ball of wax in its own right. But it's not that hard in practice. So you can think of it as a tree, or just think of it as a seed. Yeah. Okay. Cool. Let's move on. So all this type class stuff, very, very convenient in practice. Started off doing one thing, does lots of other cool things. Now here's a particular one that I like particularly because it didn't occur to us to begin with. Monads, you'll have heard of monads probably. This is the way that monads are defined in Haskell as a type class. And look what's happened to this M guy. So the signature of return, and this operation is called bind, is A to MA. So this M guy, and look, this M guy seems to take a type as an argument. Right? So it really is a type constructor. It plays the role of list of A. So M might be instantiated with list. You could say instance monad of list. Right? But you couldn't say instance monad of int, because int of A doesn't make any sense. List of A makes sense. So M ranges over higher kinded types. That's one of the things that sadly .NET and Java don't let you do, which is to quantify over higher kinded type variables. It's so good to be able to do that. And in fact, it turns out that there are loads and loads of other applications of type classes. Here's what happened to us when we implemented it. To begin with, we had no clue. Phil Waddle and Steve Block produced the idea. So then we understood what they're saying. It's kind of, they gave us this talk, and we said, that is amazing. All our problems are solved. Then I tried to implement it, so I then took sort of several years of despair trying to get a good implementation. The basic implementation is fairly easy, but you need to specialize fairly well so that you don't spend too much time passing v-tables around. So I did a lot of hangings, and now I just think, well, everybody should do it, of course. And this one idea spawned a whole a whole fertile seedbed of development and further ideas. It just generated one of those, I didn't have it, so I can call it a seminal idea, right? This Phil Waddle and Steve Block's idea. It just generated an enormous amount of interesting stuff that I hope you begin to get just a little sense of. But what I wanted to spend the rest of the time on this talk is just to give you a sense of how it fits with object-oriented programming. Right? Because now I hope you've got some visceral sense of Haskell's type classes. How does it relate to OO classes? So first thing is that type classes use type-based dispatch, not value-based dispatch. What do I mean? Look, if you look at this show class, which takes an A to a string, right, and you have some function with show A, AI or something, you could imagine that in an OO language, the v-table would travel with the A, right, and you call the show method, you call x.show, right, and that will be just fine. But in fact, the x.show story does not work for these functions that I referred to before that take an argument of some fixed type and return the overloaded type. So the example I've got here is negate of read s, right? So it takes a string and produces a value of type A for any numeric type A that is readable, where readable means you can deserialize it from a string. Now, so there is no argument of type A that I could do a method vtable lookup on. Do you see what I mean? I'm returning the value. I can't do a method dispatch on the result. I can only do method dispatch on arguments. But here's no problem in this game because I passed two dictionaries, one for read and one for num. Negate gets the num dictionary, read gets the read dictionary, and away we go. So no problem at all. It's just completely straightforward. That's very nice. So what that means is that you should think of this as more like type-based dispatch. In some languages, the so-called intentionally polymorphic languages, types are values, so that you have a function with type for all A to int, would get an argument of type T, that's the type. So an argument T, that's a representation of the type. This is like the reflection API or something. And then inside the function, you could do a type case on T, right? So it's a bit more like that in Haskell. Instead of passing the type, you pass a class, a v-table. So the v-tables travel separately from the values. In an OO language, the v-tables and the values are sort of glued together, and they sort of swim about in the ocean paired up. In Haskell, the v-tables and the values sort of float about in this sort of dance. And then suddenly, at the moment they need to meet up, bang, they meet and they marry, and good things happen. And but then the type system makes sure that the right v-tables meet the right values. But they travel completely separately. So it's rather, and in fact, you saw in this case that the v-table was traveling in and the value was traveling out, right? So they even travel in a different direction. It's very like passing the type, yes. So it's a bit more, how to say this? If you pass the type, you can do anything, right? Passing the type is almost a bit too powerful. If I pass just the v-table, all you can do is call those 5 functions in the v-table. If I passed you a type representation, then you can say, you're a list of int, I'm going to blow up the world because of that. You know, you can do something completely different depending for every type. So in a way, passing v-tables limits what you can do usefully. It's still a bit polymorphic.
Well, I did actually type of the interface.
Oh, passing the type of an interface is closer to that, yes. If you could pass a runtime representation that says, yes, this is nummable or showable. But even then, you'd still need to know, how do I now do the, in this example, you would need to pass not just the type of the interface, but you need to pass the actual read method to call. Nobody's saying it's readable. We really need to pass the interface for ints, if that was, yeah. So I'm not saying this couldn't be done, it's just not as convenient. Second thing quickly, Haskell classes are much more like, I'm sure you will recognize this, Haskell classes are more like OO interfaces. This is kind of, I guess you're partly referring to this here. A class show here with a function show A to A. Here's is more like in an OO language interface showable, and here's the show function which is part of that interface. And then in some other place where I've got a function f that takes a showable thing, well, we say showable X, right? That's what corresponds to this show a arrow. Yeah? So think, when you see Haskell class, think OO interface. But there are differences too. If in a Haskell function we can have functions with multiple constraints, that is, it must be nummable and showable. We saw that here, right? Read A and num A, that was no problem, just passed two arguments. But it's not so obvious what you do in an OO language here, because now you want to say that X is showable and nummable. You need somehow conjoined interfaces, and certainly there have been language proposals for doing that. Moreover, existing types can retroactively be made. So if you've got an old type and a new type class, like an old type int and a new type class wibble, and you just define wibble, you can make the old type int an instance of wibble just by writing instance declaration. Whereas if you've got a new interface wibble and an old type int, then it's not so clear how to make int support the wibble interface. And because the person who designed it didn't know about wibble, right? Because he worked for Microsoft, and the int designer worked for Microsoft, and the wibble designer worked for Google. Right. So this kind of retroactivity works rather better in Haskell than in OO languages. There's another sort of retroactivity I'll show you in a sec that works rather better in OO languages. So I want to spend a little bit of time on parametricity and polymorphism. Here's a way of looking at the world, the way things were back in the 1980s, I guess. Everybody wants to write polymorphic programs. That is, programs that work over values of a variety of types. OO languages do it by subclassing, right? So I write cost with type car to int, and cost will work on Fords and Renaults and so forth, right? So it'll work on values of many different types by subtyping. Parametric polymorphism, which came more out of the ML culture, makes functions that says reverse as type for all A, list of A to list of A, and it works on list of A to list of char, but this doesn't work by subtyping, it works by sort of instantiating this polymorphic function. And there are some things kind of in the middle that come area of overlap, but they kind of, there's things that you can write over here that are inconvenient over here, and vice versa. That's why OO languages grew generics, right? And it's also why ML-like languages, oh dear, ML-like languages here, like Haskell, grew type classes. Right? Because it lets us do some of the same things you can only get at with this stuff. So now the overlaps become much bigger. In effect, they do the same kind of things in rather different ways. So it's kind of intriguing to wonder whether anybody will ever make them sort of collapse completely. Scala is the closest example. I just want to show you one or two things. Let's see, where are we? It's 5 past. Well, when did we start? Did we start at 10 past? Right, so we'll finish at 10 past. There's a big trade-off. I don't see any way to avoid this trade-off between generics or parametric polymorphism on the one hand and subtyping on the other. I want to show you various examples of the way that trade-off plays out. Here's one. Haskell doesn't have any subtyping at all. So if you write a function of type tree to int, it can only take a tree. It can't take some subtype of tree. That's no good. If you want to, if you want functions to be kind of polymorphic over various types, you have to make them polymorphic, perhaps with a type class involved. So you have to, as it were, anticipate this. And this is annoying because in OO languages, you can retroactively subclass tree, whereas in Haskell, if you want this function to work over tree-like things, you have to anticipate that and write a function that says tree-like of A to int, right? So that's a place where the OO story seems a bit better. But there are lots of other, and that's to do with the subtyping thing. Subtyping versus generics, that's what forces this compromise on you. But there are other ways in which the compromise plays out. One is to do with type inference. In an implicitly typed language, like Haskell, you tend to not to write very many type annotations, right? So when you write, like f of x equals this, and the compiler infers the type. In .NET languages and Java and so forth, you tend to give the type of every binder. Every time a name is introduced, you give its type. C# is beginning to relax that slightly, which is a good thing. But the cultural heritage is functional programming language, parametric polymorphism, everything's implicit. Object-oriented language is subtyping, everything explicit. Why is that? Is it just cultural? No. It turns out it's because if you only have generics and no subtyping, the type inference engine generates equality constraints. These two types must be equal. In a language with subtyping, the type inference engine generates subtyping constraints. A must be a subtype of B. the business of type inference is to take all of these constraints and solve them. If you have a set of equality constraints, there's a unique solution. You just do unification. If you've got a bunch of subtype constraints, there's no unique solution. And that's the underlying reason, I think, why subtyping-based languages have grown up expecting everything to be explicitly declared, and Haskell and ML families have not, because we could get principal types. I'm going to ignore binary methods. One other difference that subtyping and parametric polymorphism show up is when we think about the covariant and contravariant thing. In Java or C#, if you say this increment function takes an inummable x and returns an inummable x, what that means is it'll take any subtype of inum and it'll return some supertype of inum. Right? But that does mean that if you call x.inc, right, so you can have an x which is a float and you call x.inc, is the result a float? We don't know. All we know is that it's nummable, right? So we've sort of lost the fact that we knew exactly what its type was. So in Haskell, inc has type num a to a, so inc of x certainly is a float, right? A to a, same type. So now, yeah, and this so this has a sort of pervasive effect. I think you'll find it shows up all over the place. How does this bite? Or rather, why doesn't this bite? You might worry here if you've sort of lost information. Somehow this doesn't seem to bite very much in object-oriented languages, and here's why I think it is. Here we've got x.setColor blue and x.setPosition, right? Now, here I'm using the same x, so if x was a button, then this is the same x, it's still a button. But in a functional language, x.setColor blue might return a new button. See what I mean? So more like this, I was saying, oh look, if I return x.inc, I get something I really don't know whether it's a button or not. So all I know is that it sort of has some inummable properties. So if you're working in a functional way, in which functions tend to return new values, then this business about losing information. If you said x.setColor, and then on the result of that you said setPosition, now you'd be hosed, right? Because you would just get some super type of button. So I think that the sort of, again, the imperative flavor worked rather well with subtyping, and doesn't work nearly so well in a generic setting. Okay, I want to just before we do that, let me just remark that, in fact, this problem that I've just been describing here is, in fact, troublesome enough that both Java and C# have implemented constrained generics. So do you guys use this? This is when you say, increment takes a value of type A and returns a value of type A. Or maybe I've got too. No, I don't think I have got too many A's. You have to scatter a lot of A's around these functional definitions. Where A is nummable, right? So this is very like for all A, such that num A arrow A. Right. So in fact, it's very, very close to this type now. So that's a place where C# has got a bit more complicated to try and accommodate this. So I'm going to skip all the stuff about variants, but I've got this my open question here is, if you had a language that has both generics and this kind of constrained polymorphism that Haskell has, do you need subtyping anymore? Maybe C# will get to the point at which the scaffolding of subtyping can fall away, leaving only the power of generics and constrained polymorphism. Just a scary thought, but given that its fundamental tenet of object-oriented programming in the first place was subtyping. So I think that's a sort of sufficiently open-ended question to finish up this this on. I think all I really wanted to say about, I was going to say some things I envied about object-oriented programming, but I'm not. I'm just going to finish with this, just to say that that comparing a sort of type-classy view of the world and the object-oriented view of the world I think, sort of sheds light on both. In writing this talk, which I wrote a couple of years ago, I learned some new things that I thought maybe we should add that to Haskell. That'd be kind of cool, because now I understand better something that really works better in our own languages, and certainly the reverse flow has taken place. And that maybe that big overlap that we saw eventually will somehow slip into place, and we'll discover some paradigm that doesn't mean we're constantly in a bit of tension between the two. Because I think at the moment, Scala and indeed C# and Java are getting to the point where they're sort of almost the union of everything is flowing. And if it's the union of too many things, it's just more complicated than it needs to be. So as a sort of purist, as a computer scientist, I'd really like to have the minimal set of things that do the job. Is there any other questions or comments, or indeed comments from your own experience about things that you've encountered, these kind of tensions or bumps in the road? Yeah.
Since you have no subject, can you do this vtable lookup pipeline, or do you do it?
Oh, does vtable lookup happen at compile time? Absolutely, it happens at compile time. Yes. So that is the square function lives in the library and does its vtable lookup at runtime. But if you see that we're calling the square function at type int, then we'll generate a specialized copy of it. So it's kind of like a compile time specialization of overloaded functions, and then all the resolution happens at compile time. So it's a kind of combination of both. And at the moment there's no, unlike .NET, we don't in our implementation generate specialized copies of things like square at runtime, but you could if you had a full-on JIT, which we don't. So in practice, it's a mixed economy. We try to do compile time lookup for the inner loops, and then we're just happy to do more. And it's never runtime dispatch in the same way that these are OO languages, where you're perhaps in principle looking up among a number, looking down a subclassing hierarchy. It's always select the third guy and jump to him. So it's like load and jump rather than search and search. So the dispatch is also a bit different. Any other thoughts? Okay, well, thank you very much for paying such close attention, and we'll break for how long? 10 minutes, meaning we'll reconvene at 25 past. So what I'm going to talk about in the second part is about type level functions, and it's starting to do some computation in the type system, and this will start to get to your question about adding floats and ints together. Great, thanks.